So as bacteria evolved, they become better and better at surviving and replicating and doing all the things that is chosen through natural selection. They become better at not getting killed, especially since they're so simple. They have to devise a bunch of different ways. One of the most important things that evolved early was keeping stuff in and keeping stuff out. If you're going to try to build a house, one of the first things you have to do is make sure nobody can come in and mess up your house, and your house can't spill out into the street. I don't know why it would, but I guess you have to think about that if your house is made of liquid or something. So the first thing that this guy had to develop was a way to not get messed up, especially from the stuff outside, especially in the early Earth when you had toxic nonsense going around. There had to be something to protect it. The biggest one we need to look at is the cell membrane, and membranes in general. A membrane is going to create a barrier and keep stuff in, keep stuff out. This is really important because if you can't keep stuff out, you can't maintain balance, which means you can't maintain homeostasis. So, as we previously discussed when we went over biomolecules, we know that a lipid is going to separate from water. That's why if you put olive oil and water in the same jar, it doesn't mix. So the oil is going to be hydrophobic, just like a fear or a phobia. You don't like that thing. So if you're hydrophobic, you're going to repel water, you're not going to mix with water. So we know that the cell membrane of our bacteria, or any cell for that matter, has to be hydrophobic in some capacity. It has to be able to keep water from just rushing in, or water that's inside the cell from rushing out. The way they do this is by using lipids, and they create barriers. Now, a lipid is actually composed of a string of these guys: a glycerol head and a fatty acid tail. These are just tiny little building blocks of a lipid. This guy right here is hydrophilic, and this guy right here is hydrophobic. That means the glycerol head is going to like water, and the fatty acid tail is going to dislike or fear water. So you have two things that one is going to enjoy water, one is not. So let's go back to our bacteria dude. If we were to cut a section of his cell membrane out, it would basically be arranged like this. Blue glycerol heads on top, and again, I'm just making up colors. Don't lose your mind if you see it drawn another color. Blue glycerol heads, orange fatty acid tails. They're arranged like this, where you have the hydrophilic stuff on the outside and the hydrophobic stuff on the inside. In order to maintain homeostasis in our cell membrane, we have to have a way to get stuff in and out all the time, but it can't always be a conscious effort. It has to happen naturally. Your body has to be able to maintain it. For something to happen passively, for something to happen constantly all the time, it's probably going to be ideal that it doesn't require energy. So when we transport something from the inside to the outside, or from the outside to the inside, it's called transport. You can have passive transport, which, just like the name implies, is going to have no energy requirements, basically no energy. And you have active transport. Also, like the name implies, it's going to need energy. If you have a very passive dog, he has low energy, he has no energy, that's passive. If you have a very crazy hyper dog, he's very active, that's lots of energy. For now, we are going to focus solely on the passive transport stuff. We can get to active transport later, but for now we're only focusing on passive transport, which means everything we're talking about requires no energy to go through its process. Let's start out with a simple example. I have a beaker of water. In this beaker of water are H2O molecules. They are everywhere. They are what actually make up the water. If I were to drop one drop of red food coloring into my water, it would kind of look like this initially. It would all be here, maybe a little string from where I dropped it. It would all be in one tiny dot. Over time, it would slowly disperse out. The particles of the red food coloring would spread out, and if I came back maybe an hour later, it would not be unexpected to see my water and my red food coloring molecules all completely evened out to where maybe my water is just a light pink color or a very, very faint red. I no longer have the big blob in the middle from where it hit. It is all broken. It is all gone to other places. It is slowly done what we call disperse. It is slowly diffused out into the liquid. When something does this, this is called diffusion. This is when stuff can passively spread and it can even out, because even though nothing is going on living in this beaker, there is no living water, there's no living food coloring. These are not living creatures, but the balance and the diffusion is going to passively happen. No energy required, no thought required. It's going to naturally try to even out. That's just kind of the way of the world. That's more of a physics thing than a biology thing. But it does help us understand what's going on. When some kind of particle is able to disperse and spread out like that, we call it diffusion. However, there is a specific type of diffusion that we really want to focus on for a little bit. And this is specifically the diffusion of water. This was our red food coloring. This is H2O. When you diffuse water, you have a very specific name for it. Because water is so important in all of our processes in biology, you have a very specific name for this process. You may have actually heard this. This is called osmosis. This is kind of how it works. You have passive transport. Within passive transport, you have diffusion. Within diffusion, you have a type of diffusion called osmosis. These are all still requiring no energy, and they are all still happening naturally, constantly, all the time. So if we go back to our cell membrane over here, water is very small, and because of the hydrophilic and hydrophobic properties, little water molecules that are outside the cell can make their way in and get to the other side. So if we assume this is out and this is inside the cell, they can slowly make their way in and out. However, they have to be pushed by something. It requires no energy, so there has to be some reason they are getting moved in and out. Something has to decide. I'm going to show you an example with a hill. This is the top of the hill, and I have a rock. I can push it from here, and it'll actually roll all the way down my hill, and say it ends up in this valley. It went from a high point to a low point without any energy. It was naturally flowing down. However, if I wanted to get that same stone up to the top of the next hill, going from a low point to another high point, I would have to use energy. I would have to actually push this thing up to make sure. This is going to take a lot more work than barely touching it and it just flow from high to low. So I'm going to need energy to do this portion, and I'm going to need no energy for it to go down the hill from high to low. You may have figured it out. This is basically the passive transport, and this is the active. So again, we are only focusing on processes that go from high to low. It means no energy, passive transport. So the pressure we need to be able to push water particles from the outside to the inside or from the inside to the outside is they need to go from a place of high water pressure to low water pressure. If I wanted to go the opposite direction, it would require energy. And osmosis and diffusion of water does not require any. Now, sometimes there are things that are very large. Let's say I have a big old particle that I need to get through. This is something super important. It's something I need. It's not going to be able to squish its way in between our glycerol head and our fatty acid tail and make its way all the way in. It just can't do that. However, we still need to get it in and maintain balance without energy. So we still need a way to do passive transport. Now, one of the easiest ways to get this in is going to be if we almost had a channel or a bridge going across. So think of this as a toilet paper roll, some kind of cylinder that we have pushed in between our cell membrane. Because we have this bridge, if one of these particles that's floating around here needs to come in, it can actually make its way through this bridge and it can get inside. Again, still passive, still without energy. This nice little bridge is made out of a protein. It's basically carrying our little red blob, so it's called a carrier protein. You can also call it a channel protein. And there are even proteins that will require energy that we can go over later. But these are the ones that are going to passively create this little gap that your red dude can flow through. If he didn't have this, he would be trying to bonk his way through here and not get in. But because he has access to it, he can get in and out when the cell needs whatever this thing is. Glucose, sodium, potassium, something random the cell needs to be pushed out or to be pushed in. So by now we have about enough background information to be able to do some kind of problem, or basically like a word problem for this type of scenario. Say I have a beaker. Inside this beaker is water, and then in this water is a cell. The cell is largely made up of water. You have water in a lot of components of the cell. So there's going to be an amount and a pressure. There's going to be some kind of pressure gradient of this thing. You can look at concentrations, you can look at pressures. Basically, there's going to be an amount of water in the cell and an amount of water outside of the cell. The pressure gradient or the concentration gradient is the difference from the outside to the inside. If there is some kind of pressure or concentration gradient, something has to move to equal out. This little cell right here, this happy little dude, he just wants to maintain balance. He wants to make sure that whatever he has inside equals what's outside, or else something could go wrong. If he doesn't have enough water, he'll shrivel up. If he gets too much water, he could burst. So he wants to make sure that it's as even as possible to balance out that concentration or pressure gradient. We're going to say that this is 70% water and 30% salt. Inside the cell, we have 90% water with 10% salt. So we can already see that there is a difference between the amount of water. We are going 70 on the outside, 90 on the inside. This has to even out. It's naturally going to happen. It requires no energy. If you take 90 from the inside and 70 from the outside and you want to make some kind of compromise and some kind of middle ground, this is going to eventually go to %. What's going to happen is we are actually going to pump enough water out through this concentration gradient into the salt water to where the salt water becomes more watery and the cell becomes less watery. And we're going to meet somewhere in the middle. Osmosis says 80% is somewhere in the middle. That's where we're going to meet. That's when we can stop using the concentration gradient and the differences in concentration to move stuff in and out. We have now achieved some type of homeostasis. Now, again, this is passive, so it's constantly happening. So we're not going to hit that 80 and then everything stops and shuts down. This is constant fluctuation, always going up, always going down, but always seeking to maintain that balance. It's literally like our temperature in our body when we're sick or when we're just running around. There are going to be times when we are above 98.6 and it brings it back down. There's going to be times when we're below 98.6, it brings it back up. We're never always 98.6 like a straight line the entire time. So one last set of terms for you. If you have the high concentration gradient on the outside and the low on the inside, that means we are going to pump water in until it's even. An example of this would have been if we had 90% water and 80% water. You can have, that is called hypotonic. You can have a hypertonic solution. Remember, we're talking about the solution. We're talking about the blue stuff that is in this case, probably some kind of salt water. Hypertonic solution is when we go from high inside to low outside. In that case, we have to pump the water out until we reach our equilibrium or our homeostasis or whatever we're trying to reach. Once we reach that, we are going to be in a isotonic solution. Say we split the difference between those two and the previous one and we got both of them to 85. Notice there are still arrows pointing in and out. It's still constantly moving, almost like vibrating if you were going to look at the line on some kind of graph. It's going a little above, little down, little up, little down, little up, and it's constantly pushing out water or water's getting pushed in. But it's trying to maintain that 85 for the most part, which means we shouldn't see any change in our cell. Let's go back to hypotonic. If I have a high on the outside and low on the inside, I'm moving from high to low, which means I'm pumping water in. This actually means this could burst or swell. That cell is going to have water pumped into it. It's going to change size. We are basically filling it up like a water balloon. Hypertonic means water is leaving. So if we looked at this cell and water is leaving it, we're letting water leak out of our water balloon. This is actually going to shrink. You may even say shrivel. And then finally, isotonic, because he doesn't have to worry about pumping stuff in or letting stuff out. There's relatively no change in this guy. The descriptions of high and low pressures and water moving in and out and stuff moving in and out, this is called tonicity. So in this case, we're looking at water. The water is moving out, in and out through osmosis. It's evening out with the salt water, and we're getting a hypotonic, hypertonic, or isotonic solution. We're seeking to help this guy out. We're seeking to get the 90 and the 70 evened out somehow via moving water. Now remember, we're not moving salt. Water can move in and out our membrane, so that's great. We're not moving salt at this point. We're just talking about passively letting things move in and out. It's super easy for water to move in and out. It doesn't even have to look for a protein for the most part. It can just diffuse right through the cell membrane through osmosis. A couple of real world examples. If you put stuff into your freezer, like a steak, and you don't wrap it, eventually these cells of the steak, which have water in them, will increase in size because you're freezing the water and it's expanding, and the cells burst. This is basically freezer burn. When you pull a steak out or a hamburger out you haven't seen in a while and you're like, oh my god, I forgot this garbage was in here, but I'm really hungry, and it's all white. That's why it tastes terrible and it tastes really dried out, because it's literally had these cells burst due to expanding water, and now these cells are toast, and now your chicken tastes like death. And believe me, when you eat death chicken, you will know. Like, chicken is already pretty dry. If you eat death chicken, you know, you're like, oh my gosh, this is the worst thing I've ever tasted. I'm chewing for days. It's terrible. Another real world example is blood. Blood can have hypertonic, isotonic, and hypotonic solutions, and based on the amount of sugar in the blood or any other molecules that are going to change concentration, the water is going to try to move to even it out. So if you have water moving out of the blood cells, they start to shrivel up. That's like hypertonic. Normally your blood is isotonic, which is great, but you can also have hypo, which means too much water moves into the blood cells. Either way is going to be less efficient than our normal nice little donut in isotonic, which is what we want. You can see this with grapes. We leave it outside. Now this is a super extreme, but still, compare a grape's water content to the water content on the outside of the grape in the middle of your yard. It's air. The water content is almost nothing unless it's super humid. This means the water is going to work its way out slowly, and it's almost going to leak all over everything. There's a difference in concentration. Eventually become a raisin, and it's all shrunken and shriveled up. But at the end of the day, our cell membrane is doing the best it can, and its main goal is to keep stuff from going out that we need and keep stuff from coming in that we don't. This way we can maintain balance, and we can take our energy for other, more exciting things.